Anyway, so let's chit-chat about this big idea of vectors. So, are we going? Mm-hmm. Okay, so I promise you, and here's going to be the exact sequence. There's going to be 3 vector problems on the test tomorrow, okay? And this is going to be the exact sequence of them. They're going to be on the last page, about a third of the way down, okay? If you really want to, like, plan ahead. So the first one is like the assignment that I just gave back. I'm going to give you a series of vectors, so many centimeters at so many degrees, and you're going to draw them on a tip-to-tail method. So make sure you have a protractor and ruler. Okay, so that's going to be the first problem. Okay, you're going to draw it all out, find the result, and give the angle, all that jazz. That'll be the first vector problem. Second vector is going to be something like on number 4, where we say, okay, hey, this thing is launched at 30 meters per second at an angle of 50 degrees, whatever that is. And then I'm going to ask you to find the x and y components of that. Okay? That's going to be the second problem. Okay? And you just have to know that, oh, that y is the side opposite, so that y component is going to be the vector times the sine of the angle, and your x component is going to be the vector times the cosine of the angle. Now, keep in mind what you're going to have available to you. So tomorrow when you come in, I'm going to give you a laminated version of your big dog equation sheet. Okay? You don't get your own. You get, it's the same equation sheet, but it's just laminated. So on the right-hand side, you're going to see your trig functions, sine, cosine, tangent, and the Pythagorean theorem. You just have to know how to use them. Okay? That's going to be the second problem. Third problem is going to be one like number 6 or 7. I'm going to give you 2 vectors, and I'm going to ask you to find a result of those. And I'm going to tell you right now, if I don't see the chart with the x components and the y components, I don't care if the answer is right. You are not going to get credit for that problem. So make sure that you would become one with the chart. Okay? Embrace that idea. So with that said, so let's say, for example, let me give you some hints, okay? So on number 4, you have like b plus e. This is what I would do if you said, hey, Brookham, find the result into b plus e. The first thing I would do, I'd just make a sketch, all right? It's not to scale, I'm just going to make a sketch. So I got vector b 5.75 at 90 degrees. So there's my vector b, right? And then I've got E 8.78 at 110 degrees, okay? So there's vector E. So that's 90 degrees, that's 110 degrees. So imagine this is a soccer ball, okay? Taylor is kicking the ball at 90 degrees. Zoe is kicking the ball at 110 degrees. Where's the ball going to go? Somewhere between 90 and 110, right? Okay? Now this is what we call a free body diagram. This is just a sketch of the forces. So you know, just based upon this, that your angle on that b plus e has to be somewhere between 90 and 110 degrees. Okay? That has to be it. So if you don't have an angle between those 2 degrees, you've done something wrong. Okay? So just start with that basic idea. Now, if you like the tip-to-tail method, here's vector B, here's vector E, boom, there's my result. Okay? And again, that reinforces the idea that the angle has to be more than 90 degrees. Okay? So I don't care how you do it, but I just recommend that you make a sketch. Now, here's the bigger idea. You're going to go, here's vector B, here's vector E, here's my x components, here's my y components, and that's my sum, okay? Embrace the chart. Become one with it, okay? So up above, you should have all of these calculated separately. Make sure that you have 3 significant digits in all of those calculated values up above. So what you should see on this one is that when you add together your x components should add up to be -3, and your y component should add up to be 14. So if you do that right, if you found your x components individually, And when you add those up, you should have -3 and 14. Now, here is the most critical thing that you have to do. Okay, listen to me. Listen to me. Listen to me. Here's the most critical thing that you have to do. Make this sketch. Come out here and go, I'm going to go over 3. There's my -3. And I'm going to come up 14. Okay? Make that sketch so that you have an idea of where this vector is going to end up. Then, Topher, how am I going to find that resultant? Yeah, the right angle. That's the whole point of this. Okay, that's the whole point of the story, is that we end up with a right angle. 3 squared plus 14 squared, the square root of that. Okay. Little historical fact. Y'all have learned, I'm guessing in your geometry days. I hope they at least taught you this. The magic ratio of right triangle is 3, 4, 5. Okay, 3 squared plus 4. Okay, all that. So the Egyptians were actually one of the first ones to figure that out. But then they ran into a problem, because then they said, what if it's 1 and 1? Well, then what's the length of the hypotenuse? Square root of 2. That was a deep secret that the Egyptian math community, this is way, way long ago, okay, kept secret, because everybody thought that in mathematics it should be whole numbers, and nobody knew how to handle the square root of 2. So actually the mathematicians in Egypt kind of took like this vow of secrecy. Because we don't know what it is. It's like, it's an alien number. Okay, so that was literally kept as a secret among the nerdy mathematicians of ancient Egypt. So, if somebody asked you in Trivial Pursuit, what was kept secret by ancient mathematicians in Egypt? Square root of 2. There's your answer. Okay, now this is where your calculator lies to you. Okay, and you're going, Mr. Burkham, silly. My calculator is my best friend. It will never lie to me. Okay, sure it does. Your calculator will absolutely roll you under the bus. So, I would recommend, because you're trying to find this angle right here, right? So, I would recommend, if you do this, if you take the inverse tangent of 14 over -3, so somebody take the inverse tangent of 14 over -3. Let me know what you get. And make sure that you're not in radian mode. -77.9 degrees. Now, if you tell me the angle is -77.9 degrees, what does that mean? I do not have the faintest clue what -77.9 means. Okay? I have nothing. Okay? I do not know what that means. Got nothing. I don't know if you're in the 4th quadrant, the 3rd quadrant. I don't know. Okay? This is why you have to be consistent on how you define these angles. So, what I would do, if I were you all, okay, I'm old-fashioned, I wouldn't even punch in that -3. I'd just take the inverse tangent of 14 over 3. Trust me on this one, your calculator is just going to tell you that it's 77.9 degrees. Okay? That's that angle. But you want to give that angle from that positive x-axis. So then what are you going to do? Subtract that from 180. Winner, winner, chicken dinner. Okay? And that's going to reinforce that idea that my angle has to be between 90 and 110. So that's the whole point. If you tell me the angle is like 77.9 degrees, that doesn't make any sense. It doesn't jive with the angle of those vectors. So that's why it's so important that you take a second and you make that sketch so you see where that angle is going to be. It's the best advice I can do. On that C plus F angle, that should be around 220 degrees. Okay, that's an ish, but it's around 220. On number 6, that angle should be around 75-ish. And on number 7, that angle should be around 175-ish. Okay? Is that cool?
Yeah.
Anything you want me to go over on that?
Nope.
Going once? Going twice? If you want to hold on to that and work problems using the study guide, you can. If you're done with it and you want to hand it in, that's completely up to you, okay? Whatever your preference is. But like I said, I promise you, if you hand in the test tomorrow and you haven't drawn a chart like this, you have done something horribly wrong, okay? Promise you have done something horribly wrong. Okay. So let's chit-chat about the test. So do you think I'm going to ask you what is the difference between the vector quantity and the scalar quantity?
Yeah.
Yes, it's going to be at the top. It's going to be the first question on the top of the last page. Okay, and I'm going to ask you just that. What's the difference between a vector quantity and a scalar quantity? Okay?
Scalar only has magnitude.
Scalar quantity only has
Magnitude.
magnitude. Vector quantity has
Direction.
magnitude and direction. I promise you, it's going to be you're going to flip to the last page. First question at the top. Okay, or somewhere around the top. Okay, that's going to happen. Let's say that I gave you a position time graph that looked like this, and then said draw the velocity time graph that matches that motion. What would you do?
Horizontal line.
Straight horizontal
Horizontal
line?
line.
Okay, why?
Because they're both constant velocity.
Okay, so back up the bus. What does the slope of a position time graph give you? Velocity. So if the slope is constant, therefore the, and you show a constant velocity as a horizontal line. Okay? Now, if I had something like this on the position time graph. Go away. Whoa. Back up. So if I gave you that as the position time graph. So first off, Jack Green, is this object speeding up or slowing down?
Position time graph.
Yep.
It is
You had a 50-50 shot.
slowing down.
You say that with no confidence.
Say it with confidence.
Say it with confidence.
Slowing down
How do you know it's slowing down?
because
The fact that I didn't yell and scream is not an answer.
because it's starting to like level off and become constant
Okay? And the slope of a position time graph gives you.
velocity.
So as the slope becomes smaller or more shallow, that means the velocity is becoming
Smaller.
small. I'm approaching 0 meters per second, right? Because how do you show an object that's at rest on a position time graph?
Straight slope.
Straight horizontal line, right? So if it, as it's approaching that straight horizontal line, right, it's slowing down, okay? So how can I show that an object slowing down with positive velocity on a velocity time graph, assuming that we have uniform acceleration? Something like this? Go with that.
Yeah.
Okay, so this shows it's starting fast, still positive, so there you go. Now, Dime, on that position time graph, did that object change direction? Why not?
Because it didn't, the slope didn't change signs.
There you go. True or false? If the slope of a position time graph changes, the object changes direction.
False,
Why?
because it has to change sign, not just change.
Yes, because if I just change the slope of the position time graph like that didn't change direction, okay? Because the slope didn't change sign. Now, if I said, if the slope of a position time graph changes sign, then would that be a change in direction? Yes. So all this thing is doing is still going in the same direction, it's just slowing down, okay? It's approaching 0 meters per second. And that's what this shows here. Now, I promise you on the test, one of the things I'm going to ask you to do is find the instantaneous velocity on an object that's accelerating. Okay? So what I might do is I'm going to go to this position time graph and I'm going to say, okay, you're here at the 4-second mark. And I'm going to ask you, what is the velocity at exactly 4 seconds? Okay? So what are you going to have to do?
Tangent line.
Draw a tangent line. So you're going to take a ruler, and I will give you this point in time. Okay, I'm going to say 4 seconds, whatever that is. So you're going to come up here at that 4-second mark, and then you're going to have to imagine that this is part of the circle. And then you're going to draw that tangent line where it's going to touch that circle at exactly 1 point. So you're going to have something like this. Okay? Now, let's say that this is 4 seconds and 12 meters. So could I do this? This point is 12 meters, 4 seconds. Could I just take 12 meters and divide that by 4 seconds and go, ooh, physics is easy. My velocity is 3 meters per second. I could do that. You said I could. You sure? Positive?
Yes.
Why not?
That's just a point. You need to find another point.
Ah, how many points do you have to define the slope of the line? 2. Okay? Because if you just take 12 meters and divide that by 4 seconds, which is really simple, you're going to say that no matter what point goes through that line, it's going to have the same slope of 3 meters per second. Seem logical? Not in the least. So, could I use that as 1 point? I could use that all day long. I could say, okay, I'll play your game. 4 seconds, 12 meters. But then I'd have to pick another point on that line. So tomorrow, when you get done with the test, if you have not taken a ruler and drawn a tangent line and found the slope of that line, ask yourself that question when you hand in the test. Did I draw a tangent line and find a slope? If you answer no to that question, don't hand in the test. Okay? Don't hand in the test. And I'm even going to tell you, hint, better use a ruler. Okay? I will tell you specifically when to use the ruler. Okay? I'm not even going to make it ambiguous. I'm going to say, hint, use a ruler. Okay? So, that's what's going to happen. All right. Speaking of velocity time graphs, let's say that I do this. Here's my velocity time graph. Did the slope of my velocity time graph change sign?
No.
It,
Yes.
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 Look at the line.
I said yes and you looked confused.
okay. Pretend that you are all in a math class. Okay? Pretend you are in a math class. A line comes down like this. What's the sign of that slope? Negative. So here I have negative acceleration. True?
That is true.
Am I speeding up or slowing down? Slowing down. How do you know?
Velocity's positive.
Velocity is positive. The acceleration is.
Negative.
They have opposite signs. You are slowing down. Is there any exceptions to that rule? Can you ever speed up if velocity and acceleration have opposite signs? No, 0, zip, none. Can't do it. Okay? The other way that you can view this is this line is approaching 0 meters per second. Okay? That's the other way that you can view it. Oh, the line's approaching 0 meters per second, therefore I am slowing down. If you're into signs, look at the signs. Oh, they're positive and negative, it's slowing down. Okay? So here's the $1 million question. At this point, does the slope of the velocity time graph change sign? Yes, because we go from negative slope to positive slope. So here I have positive acceleration. True? Good with that. Now, did the object change direction at the bottom of that V? Why not? Seems like it should.
0.
What do you have to do to change direction? Slow down,
Stop.
Speed up.
speed back up. Did we ever stop? No. What did we do? Slow down and then you sped back up again. Okay? So all that happened is that I was cruising along, stopped, then I sped back up. Okay? That's all that happened. I did not change direction. If I wanted to show a change in direction, what would I do?
Cross zero.
Now, if I wanted to show a change in direction, would I go past the reference point, or would I go through 0 meters per second?
0 meters per second.
That 0 is not the reference point, okay? That's just 0 meters per second. So, can you tell where, if all I gave you is that velocity time graph, could you tell where I am relative to the reference point? No, the only thing I can tell is that I have positive velocity. That's all I know. I don't know where I am. I just know that I have a positive velocity that's slowing down, and then I speed back up. Okay? You cannot tell where you are on a velocity time graph. If I were to find that area underneath that velocity time graph, what would that give me?
Displacement.
Displacement. Okay? Can displacement be negative?
No.
Yes.
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 Displacement can be negative.
Yes, displacement can be negative. Is displacement a vector quantity? Yes. Look at the CART lab that you all did. You went from 0 to 3. Okay? Oh, positive displacement. Because so there's two ways you can do displacement. You can find the area on a velocity time graph, which could be a negative velocity multiplied by time. Or what's the other way that you can subtract quantities to calculate displacement? Final minus initial. So if this cart goes from 0 to 3, oddly enough, I'm going to take my final position, which is 3, subtract that from 0, check my math, I get 3. Now, on the way back, what's my initial position? 3. What's my final position? Take 0 minus 3, you get negative 3. Okay? So don't confuse distance with displacement. Distance is the scalar value. How far did you go? 5 meters. Cool. Okay? I just know you went 5 meters. I have no idea which direction that you went. But if you say, hey, I went 5 meters at 0 degrees, or I went negative 5 meters, that then makes it a vector quantity. Okay? So that's the difference. So yes, you can very much have negative displacement. You can have negative velocity. True or false? Negative velocity means that you are going backwards. Nope. The only thing you know is that it has a particular direction. Negative does not mean that you are going backwards. True or false? Negative acceleration means that you are slowing down. Could it mean that you're slowing down?
Yeah.
But you're only slowing down if you have negative velocity and positive acceleration. Because they have to have opposite signs. So you can slow down with negative acceleration, but only if you have. Now, can you speed up with negative acceleration?
Yeah.
If you have.
Negative velocity.
Now, how would that look like? What would that look like? Negative velocity and negative acceleration, what would that look like on a velocity time graph?
Down in this one, and then it would be going this way.
Nick's over there doing okay? So, Nick, is this the international sign for a negative sloping line below the x-axis on a velocity time graph? Okay. Anywhere in the world you go, you do this. Oh, negative velocity, negative acceleration, velocity time graph. Cool. Nerd power, rock on. Okay. So yeah, you got that action going, right? Okay? That's it. Negative velocity, negative acceleration, you're speeding up. Okay? All right. Cool with that. Let's say I gave you, hypothetically, a position time graph that, let's say that's 4 meters and we have something like this. And that's 2 seconds. Let's say that's 5 seconds, and that's something else. Okay? how many times, that's a position time graph, okay? It's a position time graph. How many times does that object change direction?
Twice.
Why twice?
Because it zeroes out twice.
What is
The slope.
it zero
The slope.
mean? The slope.
Mm-hmm.
How do you know? Let me give you a hint. It rhymes with the word tangent line.
With what?
Use a word that rhymes with tangent lines.
Tangent lines.
Have a slope of,
Zero.
okay. So, at 2 points, you can draw tangent lines that have a slope of 0. Okay? Or if you're a math nerd, you have a relative max, okay, right? Now, did it change direction there?
No.
No, what did it do? It slowed way down, right? How do you know it slowed way down? Slope became, or shallow, less steep, okay, more freshman, however you put it. Okay, are you going faster in this region or in that region? Region 1, region 2? 1, how do you know? Slope is?
Deeper.
There's a more rapid rate of change in your position, okay? What if I ask you to calculate the overall average velocity for the trip? I want the average velocity for the entire trip. You all did this calculation on the very first lab that you did with the cart. Anybody remember how you calculate average velocity? It's overall something minus overall something divided by something.
Overall displacement.
That's right. So what's my overall final position?
0.
0. Okay, I end up at the reference point. What's my initial position? 4 meters. And that took,
10 seconds.
so on, what I'm saying then is on average, my velocity is
Negative 0.4
-0.4
meters per second.
meters per second. So if you have a position time graph and you're asked to calculate average velocity, it's the overall final position minus your initial position divided by time, okay? And I might say, oh, what's the average velocity in this interval? All it is position final minus position initial over time, but don't make that wrong. You're going to have problems involving distance equals velocity times time. What's the only time you can use distance equals velocity times time? When you have constant velocity. So like I couldn't do that if I throw this apple up in the air. Why? So, because as soon as it leaves my hand, what does it start to do? Slow down. Does it change direction? Yes. Okay, pretty much. But it'd be really weird if it didn't. Like throw it up or what happened? I don't know, through a hole in the ceiling. Okay? So yeah, it changes direction. So what do you know about your velocity? It is always changing, right? So I can't use distance equals velocity times time. So you're going to have a problem like this. I'm going to say, okay, somebody pick an African animal. Whatever. Okay, so here's a horribly drawn artistic elephant. Okay.
Conservative.
And he's moving at, somebody pick a number between 5 and 10.
10.
10 kilometers per hour, right? And he has to walk, somebody pick a number between 50 and 100.
100.
Between 50 and 100. 75 meters. Okay? So, Eddie the elephant is moving at 10 kilometers per hour, and Ellie, he's got to walk 75 meters. And I want to know how long this is going to take. Okay? Now, you have 10.0 kilometers per hour. How many significant digits is that? 3. You have 75.0 meters. How many significant digits?
3.
3. How many significant digits do you think your answer should have? Three. Not a difficult concept, okay? Now, you have 75 kilometers per hour. What are you gonna have to do with the kilometers per hour? Change it to meters per second. If you hand in the test tomorrow and you have not converted kilometers per hour into meters per second on one of the problems, you have done something wrong, okay? Promise you, you're gonna have to do that conversion. So, I've got 10 kilometers per 1 hour. 1 kilometer is 1,000 meters. 1 hour is
3,600 seconds.
3,600 seconds. If you want to get clever, mark off the zeros, multiply by 10, divide by 36. So somebody take 100 and divide it by 36.
That would be 100 over 36.
Two point what? Meters per second. When you do this conversion, make sure that you keep at least that number of digits when you do that conversion. Don't round this to 3, do not round it to 2.9. You keep at least those 3 digits. Now, at this point, there are 3 different ways that you can work this problem, okay? I'm going to show you all 3. I don't care which one. Okay? So what's one option that we could do? Maggie, what's one thing that I could do to solve this problem?
What are you trying to solve?
I'm trying to find time. I'm trying to figure out how long it's going to take Eddie the elephant to walk the 75 meters at 2.78 meters per second. Keeping in mind that distance equals velocity times time.
Plug in 75 meters.
No, wrong, bad, no,
Don't do that.
don't do that.
Plug in the volts.
Nope. Do not start with the word plug. Start with the word that rhymes with olve.
Solve
Solve.
for
Solve the equation for
velocity. Just kidding. I'm joking. We're time. We're time. Thank you. I was just,
You were just seeing if I was paying attention?
Yeah.
Okay, did I pass?
no.
Sadness. Okay, so time is distance divided by velocity, right? So if you're an equations kind of person, I'm going to take, in this case, 75 meters and divide that by 2.788 meters per second. Now, if you do this wrong, you mark my words, this is what you're going to do wrong. What do you think you're going to do wrong?
Meters per second, yeah, whatever that is.
No.
Oh, not that wrong.
Here's what you're going to do. Not that wrong. You're going to take velocity and you're going to divide that by distance. You're going to go meters per second and you're going to divide that by meters and you're going to go, oh, I get seconds. If I do this wrong, if I take meters per second and divide that by meters, do I get seconds?
No.
No. What do you get?
Meters.
I get 1 over seconds. 1 over seconds is not seconds. Okay? And you all sit there and you go, Mrs. Burkamp, you would never do that. Don't be silly. Okay? But if I take meters and instead of dividing by meters per second, what can I do? Multiply by,
Seconds over meters.
now I get seconds, that's what I want time to be. Okay, so somebody take 75 and divide that by 2.78.
27.0.
27.0
Good.
seconds. Okay? That's option 1. I'm an equations kind of person, Mr. Burkamp. That's my wheelhouse. The other option that you can do is you go, I live for ratios. Okay, I'm the president of the ratio club at Mays High School. Cool. Okay? So remember, you're traveling at 2.78 meters per second. That's what that number means, right? Per second, this is how far you're going. So you could set that up and go, oh, that's 75 meters over X number of seconds. Now, how do you know, and this is the beauty of the ratio, okay? How do you know that your answer has to be more than 1 second? You're moving more than 2.78 meters, okay? So that's the beauty of the ratio. You look at it and go, well, I'm only moving about 3 meters per second. I gotta move about 75 meters. I gotta figure my answer is gonna be more than 1 second, okay? That's one way to look at this. So then you can cross multiply, take 2.78 times x equals 75 times 1. Oddly enough, you're gonna get the same answer, okay? So if you like ratios, look at this ratio. Now, you go, oh, Mr. Burkamp, I love geometry. I like rectangles. Okay, so how could we show this on a velocity time graph?
Sorry, I'm listening.
I know you are. So how can I show that on a velocity time graph? A horizontal line at 2.78 meters per second. Now, how does the 75 meters become part of this problem? That is that's the area, right?
Oh, yeah, it's the area.
So how do you find the area of a rectangle?
Length times width.
You can do this as a geometry problem. What's the area of that rectangle?
27.
35 meters.
27.
What's one dimension?
2.78 meters.
2.78 meters per second. What's your unknown dimension?
X.
Time. Okay? There you go. I don't care how you work the problem. You can use equations, you can use ratios, you can do geometry. Okay? I care not. Just pick the method that works best for you. There's probably going to be 2 or 3 problems like this. Okay? So again, if you get done with the test and you haven't done distance equals velocity times time, you have done something horribly wrong. Okay? There's going to be questions on that lab that I just gave, on the cart lab, where it rolled in, hit the wall, and bounced back. Okay? So what I might do is give you a velocity time graph that looks something like this, and say, when does it undergo its maximum acceleration? Now, here's the kicker. When I'm talking about acceleration, am I only talking about something speeding up?
No.
No. So acceleration, what does that mean? What is changing? Velocity. That's all you know. Okay? So get out of your minds right now. If I say, when is the object accelerating? Get out of your minds right now that, oh, Burkamp just wants to know when it's speeding up. Okay? If I'm talking about acceleration, I'm just asking, hey, when is the velocity changing? Okay? So if I gave you that graph, when is that object going to undergo its maximum acceleration? The shallow part of the graph or the steepest part of the graph?
Steepest.
Steepest, because the slope of a velocity time graph gives you acceleration. So from here to here, there's 0 meters per second. So from here to here, what's the object doing? Speeding up or slowing down? Slowing down. So you can put like a down arrow there. After it crosses 0 meters per second, is it still slowing down?
Nope.
No. Okay, you can't slow down more than 0. Okay? Once you hit 0, what's the only thing that you can do?
Speed up.
Speed up. Okay? All right? So that's the type of questions I'm going to ask you about. So make sure that you go back, look at that cart lab, look at your velocity time graph, know what's going on, when is it speeding up, when is it slowing down, when is friction the dominant force that's making it slow down, when is the spring the dominant force that's making it change speed, when does it hit, when does it leave, that type of thing, okay? So those are the big things, all right? So what I have for you to help you get ready for the test.
Friction. It has negative friction.
So you've got 3 pieces of paper. So the first one is just telling you, hey, these are the topics that are going to be on the test. Okay? That's that. The second one is a set of problems, okay, that you should be able to do. position time graphs, vectors, that type of thing, okay? And then the third one is the answer sheet, okay? What I would recommend is that you sequester this away and not even look at it until you work this, okay? Because what happens is I say, question number 1, can a car change direction with constant velocity with uniform acceleration? And then if you read my answers right away, you go, man, Burkamp's got that one right. That's good. No. Okay. What I would do is I would literally treat this as the test. I would work the entire thing. Then I'd look at this. Okay? Now, when you get to this last question with vectors, notice that I've got this nice little chart drawn here. Guess what? That's what I'm going to expect you to do on the test, okay, is this level of work, okay? And yes, there's tangent lines that you have to draw, okay? If you're going, man, I don't remember tangent lines, go back and look at that roller coaster sheet that you have, okay? So, what I would recommend, if I were taking this test, I'd work through this, okay? Then I'd check everything against that. I would go back and I would look at, you have all your assignments back, okay? If you've missed anything, go, wow, man, I didn't remember that. How did I screw that up? Because in case you haven't noticed, I correct your homework, okay? So you know what you've done wrong, right? So go back, look at this. This has to become repetition. So if there's problems, you go, man, I'm not feeling good about tangent lines. Guess what? Work on drawing tangent lines. If you're going, man, I don't get the whole vectors thing, work your vector problems, okay? Make sure that you understand scenarios.
I'm sorry.
Are your hands still wet or are you hot?
Yeah, just, yeah.
Yeah,
Yeah,
okay, all of the above?
yeah.
Okay, so let's say your hands are changing direction, okay? What would that look like on a position time graph, okay? You know, I'm just saying hypothetically, okay? So that's, don't hit Jack, that's my job.
Sorry, yeah, man.
He's been on my encore for 4 years, I'll hit Jack, okay?
I'm sorry.
All right, so I'm done.
You've had it for all 3 years.
Yeah, it's been in my encore.
That's
Oh, yeah.
so not fair.
Taylor, Jack, yeah, I've had both for a few years. So, for God's sakes, I've taught in this room since 1996, so that is anything. Okay, so I'm done. I would recommend that you use the time wisely. I know some of you have busy schedules, so here we go. What?
Today when I went to talk to Miss Manning about this senior. I'm so tired. Okay. She goes problematic and I go, oh, you should do our
Turn on.
missing.
You want me to bring you dinner?